Hi, my name is Andrea Selko, and I will be presenting my honors thesis research on exploring the synthesis of Anisucoumaramide. Anisucoumaramide is a molecule that belongs to a class of molecules called coumarins. Coumarins have the chemical structure that you can see here, and this is the numbering that we use when we talk about them. Because of the chemical structure of these molecules, which is a benzene ring attached to a pyrone, these molecules have a certain amount of chemical functionality in which they have the ability to engage in hydrogen bonding, electrostatic interactions, pi-pi interactions, and hydrophobic interactions just from the backbone perspective. On top of that, these molecules can be diversified by adding different side chains. So these side chains will give it even more properties on top of the properties that the backbones already possess. For example, here at the 4th position, we have the addition of an alcohol, which causes coumarin, which is normally insoluble in water, to be soluble in water in a slightly alkaline condition. Because of this molecule's, the backbone itself has a certain ability to engage with other molecules just because of its chemical structure. And on top of that, adding side chains gives it even greater range of properties. These molecules have a lot of pharmaceutical applications. So some of the versatility that these molecules have has to do with their ability to act as anti-inflammatory agents, antimicrobials. They can be used to activate immune cells, and they can be used as anti-cancer drugs, just because of how they can be manipulated in different ways. Another thing that they can be used as is an MAO-B inhibitor. So an MAO-B inhibitor is a molecule that inhibits the activity of MAO-B. And MAO-B is an enzyme that's increased activity is correlated to the increased production of plaque on certain cells. And as you can see in this flow chart here, like through that chain of events, and this increased accumulation of plaque is what is correlated to the progression of neurodegenerative diseases, such as Alzheimer's disease or Parkinson's disease. And so with Alzheimer's disease specifically, how we treat that disease is we introduce an inhibitor that cuts off that pathway so that the disease cannot progress as fast as it otherwise might. Anisucoumaramide, which is the molecule we talked about in the title, is a newly discovered coumarin that has MAO-B inhibitor potential. This molecule was discovered in a paper in 2017, and it's isolated from a plant called Clausena anisum-olens. In the paper that isolated this plant, however, it had a very low yield. They were only able to get 2 milligrams from 22.5 kilograms, which is approximately the same as considerably less than 1 ounce from almost 50 pounds. So, but from what they did get from that, the 2 milligrams, they did some tests and they saw that this molecule has MAO-B inhibitor potential. And so the focus of my research has been to try and synthesize this molecule in a lab so that its biological properties could be further studied and just see if it could work as a MAO-B inhibitor or other biological properties as well. The big picture for this molecule, so since it's such a large molecule, the synthesis is broken down into 2 halves where we have this part here, which is the coumarin backbone, and then this blue part is the furanone side chain. And you're going to create the 2 halves separately and then bring them together at the very end. So we're going to talk through the blue part, which is the furanone side chain first. So we're going to start with this starting material and methylate the alpha carbon here. This is followed by an allylation reaction, which adds the allyl group here. Then we're going to do a decarboxylation reaction. Then we're going to bromate this carbon here. And then we're going to substitute that bromine with an alcohol and then protect that alcohol. And then we're going to transform this double bond, this alkene, into this 3-membered epoxide ring. And then we're going to pause here, and because I really want to highlight this reaction, this takes the 3-membered, this is a novel step in the synthesis, and it takes the 3-membered epoxide and expands it to the 5-membered furanone ring. One of the previous members of the Felix lab actually found this reaction And it's just very interesting and unique. And so I really want to highlight it because we're going to talk about it later too. And then we're going to do this cross-coupling reaction. And then we're going to reduce the alcohol on the carbonyl carbon. And then we're going to substitute that with tosylate. And we're going to eliminate, deprotect the oxygen that we protected way back, and then substitute that with tosylate. And that's how we get to the furanone side chain. So the first step in all of that is the methylation reaction. You take the starting material and you just methylate the alpha carbon. It's a very straightforward reaction, and so I was able to get a pretty good % yield. It was one of the first things that we did in the lab. The following step is the allylation reaction, and this step I got considerably less favorable % yield. This was frustrating at first, but like eventually we figured out that it's probably because the THF had peroxides in it, which essentially means that it was expired, and its reactivity, the presence of the peroxides in the THF was affecting the reactivity of the reaction. And if I redid this reaction with a fresh batch of THF and starting material, I should get a higher % yield. And then also another thing that I worked a lot on is the ring expansion model. And the premise of the ring expansion model is that because that step is so novel, we don't want to waste material that takes multiple steps to create, just trying to iron out the details of this reaction. And so instead we use readily available, commercially available this material like this alcohol here, and we iron out the details, figure out the reaction conditions that make this reaction work best before we get to that step in the synthesis. So we use this allylated alcohol and protect it using tert-butyl diphenyl silyl chloride to get this molecule here. The yield is not determined because one of the final steps in this reaction is to protect the methanol, which or it's to use a methanol to kind of use up the rest of the tert-butyl diphenyl silyl chloride that is in the solution. And so what you get is you get this mixture between the protected alkene, which is what we want, and then the protected methanol, which is just very chemically similar to the alkene. And so we don't spend the time to separate them that we could, just because the next step naturally separates them and makes the molecule that we want much more different than the methanol, and they're very easy to separate after that. So yeah, that's why we don't have a yield though to report here. The next step is the epoxidation step, which I kind of just implied, in which we take that alkene and we use NCPBA, we get that 3-membered epoxide ring. However, we have a very low yield, and there's two theories as to why that could be. The first is kind of going off of what I just said, where this isn't actually a pure solution of the protected alkene. Instead, what we have is a mixture between the protected alkene and the protected methanol. And we might not be, since we don't know exactly how much of the alkene we have, the numbers that we're using to predict how much of the epoxide we should get might be off. We might be overestimating how much we should see. And so we're getting numbers that are a lot smaller than what we expected. Another theory is that the protected alkene I made it in February of 2020, and then we had to leave, and I wasn't able to do the epoxidation reaction until this fall. And there's a chance that the molecule started to decompose, the integrity was compromised over that time period. And when the epoxidation reaction went through, like when we did that reaction, it just didn't have the same reactivity it might have had if it had been a fresh batch. So, and then finally, for the model, we got to the furanone step. We ran this reaction a couple times. However, we did get one spectra before purifying it that was promising. It had peaks that were different, that were interesting. But after purifying it, just because of the technique and there's so little to work with, we lost it. And so I would definitely want to try and run this reaction more and see if we could get just more products, purify it, and better spectra to analyze. But yeah. So that was all of the furanone synthesis that I've done. So now we're going to shift gears and look at the coumarin synthesis. So this all starts with this 2,6-dibromoanisole, which after doing a cross-coupling reaction, we have the dihydroxyanisole here. And then we're going to add an aldehyde, and then we're going to do a Wittig reaction, and then we're going to cyclize it to be the coumarin that we're looking for using riboflavin and heat and light. I spent a majority of this Jan term working on this cross-coupling reaction. And so what you can see here is that we tried out, so because the paper that we looked at, they only used this reaction to take one bromine and transform it on an anisole to one hydroxyl group. But we wanted to do a dibromine to dihydroxyl. And so we had to figure out what reaction conditions would be the most favorable for this reaction to try and get the product that we're trying to get. So we tried different ligands, which you can see here, ligand 1 and ligand 2. And we, ligand 2. And we tried different equivalences of the potassium hydroxide, which is the base, and just to see what like mixtures of things might get the most efficient reaction. And after running all of these reactions, we started to get spectra that looked consistent. There were different levels of purity, like some of them had a lot of hexanes mixed in the solvent. Others just had these like weird peaks, so we weren't really sure, but they all started to kind of have a trend with the same general pattern. And so this is what the proton NMR started to look like consistently. So a proton NMR, what that is it's essentially telling us information about the protons that aren't drawn on these structures, but they're present. It tells us information about what type of chemical environment they're in, and then we can use that information to piece together what molecule we're actually looking at. Because we know what we want to be looking at, but we need to make sure that what we actually produced is what we were trying to produce. So after looking at this NMR, it looks very different than the NMR that we took of the starting material. So we know that there was a reaction, but what we don't know is if what we're looking at is an intermediate, which is here, where only one of the bromines came off and was replaced with a hydroxyl group, or if we're looking at the product that we're trying to get with this dye substitution. So looking at this here, these are hexanes that are trapped in the solvent, and then we have these protons, which are correlated to the aromatic rings. They're somewhere down here. And then this one, which would be on this carbon here. But we don't know exactly which molecule we're looking at. We just know it could be either one. So we have to do another spectra. So the carbon NMR is a lot like the proton NMR, in which it is telling us information about the chemical environment, but instead of with protons, it's telling us about the environment the carbons are in. And just looking at this, there's kind of a lot of peaks, but we can immediately disregard these because we think that they have to do with the hexanes that are just trapped in the solvent. And then this peak is just a solvent peak. And so that gives us seven distinct peaks outside of that to analyze. Because the product that we're trying to get has a certain amount of symmetry, these carbons would be in the exact same chemical environment, and so their peaks would overlap. So we wouldn't, if that molecule was present, we probably wouldn't see a unique peak for every carbon. So the fact that we see 6 peaks in the aromatic ring is kind of starting to indicate that every carbon in the aromatic ring is in a little bit of a different environment, and so it's showing up in a little bit of a different area. But just to be sure, we wanted to run another spectra, so we ran a GCMS. GCMS, they usually give information about the molecular weight of molecule. So here, but they also tell you something extra, especially if you have bromine involved. And so if you look at this peak here is where we're going to really want to focus our attention. There are 3 peaks within that signal, right? And that is because there are 2 isotopes of bromine. There's a heavier one and a lighter one. And that means that on this molecule, there's 3 options. So we have the option where both of the bromines are the heavier isotope, both of the bromines are the lighter isotope, and then the third option, which is twice as likely to occur, that one bromine is heavier and the other one is lighter. And so that's why we see this peak right here in the middle is twice as tall as the 2 side peaks. So when we did the GCMS of the material that we created, we saw these 2 twin tower kind of like peaks in the signal. And that really confirms that what we're looking at is the intermediate. because on this molecule, you can have either the heavier isotope or the lighter isotope of bromine. You can't have both, but you can have either one in equal amounts, and that's why there's those two peaks. So yeah, that was really exciting because it showed that our reaction was working and it was going in the right direction. We just needed to, we just need to figure out how to get that second bromine off, which kind of leads me to the future directions. So obviously with like the allylation reaction, one thing that I would want to do is try and improve the efficiency of certain reactions, the allylation one. I know that if we just did that reaction with a fresh batch of THF, we could probably get a higher percent yield. I also would want to continue to develop the ring expansion model just to keep doing that reaction that creates that furanone ring more and try and get the reaction conditions figured out and see what's best for that reaction. And then I would want to continue to develop the cross-coupling reaction, which would primarily mean putting that mono-substituted or mono-bromo-substituted anisole back under the cross-coupling reaction conditions, seeing if we can get that second bromine to come off. Maybe it just needs to be reacting for longer, or if that doesn't work, trying different ligands, trying different solvents, just changing the conditions, seeing if there's a way that we could get the product that we're looking for. So yeah, I would like to acknowledge the Welch Foundation, the NSF MRI grant. Laurel, Madison, and Christina did a lot of the background and like foundation research that I built my like research off of. So I definitely want to give them a shout out. And Dr. Felix for always listening to my talks and answering all my questions and helping me with my research. So thank you.